Hello everyone, this is Indrani. Today I am going to deliver lecture on the phase lock loop, which is in the subject name of IC applications, or it belongs to the linear and digital IC integrated circuits. So first, what is the importance of the phase lock loop? Here the importance of the phase lock loop is generally so many applications we require whatever the device is there, the device has to be tuned to the incoming signal frequency as well as the phase. Then only we can observe what is the type of signals we are getting and we can extract basically some information. The best example I can tell here is the FM radio. Suppose if I tune to some other frequencies rather than 98 point, my required frequency is 98.3 megahertz, right? So exactly at 98.3 megahertz, I will get the voicey type of signal. I can able to hear the corresponding voice. Suppose if my radio is operating at some other frequency of 90 megahertz frequency, or if it is operating at 99.7 megahertz frequency, at that time I cannot listen the voice which I am getting at 98.3 megahertz. So in the radios, what we are doing, we are just tuning the corresponding frequency. If the frequency is tuned to 98.3 megahertz, then only I can hear the voice, right? So here, in the similar fashion, for the satellites, radio communication, radar systems, as well as the wireless communication systems, there is a requirement of the frequency and phase signal tuning is required. At that place, I can use the phase locked loops. Phase locked loops. If you observe the name of that phase locked loops, phase locked loop. So here, first thing, some looping type of operation is going on. Okay. So later, when the corresponding looping, in the looping, here this is basically this phase lock loop is a control system type of arrangement. So in the control system, what will happen? And particularly this one is a closed loop control system. So closed loop control system means there is a certain amount of feedback will be there. Based on the feedback, the circuit properties get changes and it will generate a new amount of the output, right? So in this phase lock loop here, basically let us move to the this thing. So in this phase lock loop, what are the output signal is there? The output signal of the phase lock loop always try to match with the input signal frequency and the phase. Suppose if the output signal is not matched with the input signal frequency and the phase, always whatever the closed loop circuit is there, it will reduce the difference between the input signal and the output signal till the input and output signal having the same frequency as well as the phase, like that continuous looping type of operation will be goes on, right? So before going to the block diagram and the corresponding feature description and the corresponding internal block diagram of each and everything, so let us see what is the basic applications and let us go to the circuit model. So here the PLL can be mainly widely used in wireless communication, RF applications. Next, in the Wi-Fi routers, wherever the frequency and phase tuning is required for these type of applications, we are using the phase locked loops. And for the broadcast radio, walkie-talkie radios, televisions and mobile phones, we are using the phase locked loops. So as I said you previously, this phase locked loop is a control system that generate output signal whose frequency and phase is related to the input signal frequency and the phase. Both should get a match. And in addition to that, what are the other applications? Here is generally satellite applications, airborne navigations, next FM communication systems, and in the computers, we are using the we are using the circuit models of the phase locked loops. So what are the phase locked loops are there? Still now also the research is going on the PLLs. So for the researchers also, they should know what is a basic operation with respect to the phase locked loop, right? So let us go for the next thing. So in the phase locked loop, this is the basic block diagram of the phase locked loop. So it is having the phase detector, low pass filter, amplifier and voltage controlled oscillator. For this phase detector, we are giving the input signal for the phase detector, which is having the voltage of Vs, amplitude of Vs and the frequency Fs. And this one is generating some amount of error voltage. So here, to generate this error voltage here, if you observe for the phase detector, I am giving two inputs. One is the input signal and another one is the VCO output. VCO output. So which will generate the corresponding voltage is V0 and the frequency is F0, right? So here the phase detector is a comparator type of circuit. So what is the function of comparator? Just it will do the comparison of the respective two inputs and it will generate the concerned output value. So here, in addition to that, this phase detector works as a multiplier. So in this multiplier, it will generate the corresponding output voltage, which is the some error voltage of VE can be generated, and in addition to that, it will generate two set of frequencies, that is the Fs minus F0, difference between the frequencies, and summation of the two frequencies will be generated in the output of the phase detector. Here for the phase detector, we are giving the two types of inputs, one from the input signal and another one is the VCO output. Okay, so here the phase detector will do the comparison of both the signals and it will generate the output signal, which is the error voltage VE, having the frequency ranges of difference between the two incoming frequencies and the summation of the two frequencies. So later it has been passed through the low pass filter. What is the function of the low pass filter? The function of the low pass filter is it will filter out the high frequency components and it will allow only the low frequency components, right? So in the similar fashion, the low pass filter will generate the output of the low pass filter is it will filter out the high frequency component. What is a high frequency component out of these two? This Fs plus F0 is a high frequency component. So this frequency component gets removed and it will generate the output signal which is having the frequency of Fs minus F0 and the amplitude of VE, error voltage VE, right? So what are that error voltage is there? The amplitude of the error voltage is very, very small, right? So that's why that has been given as the input for the amplifier. What is the function of the amplifier? It will amplifies the input signal, means amplifies the input signal means it will improve the strength of the input signal. The input signal strength will be improved by the amplifier circuit. So that's why here the output of this amplifier is represented as a VC. VC means this is nothing but the control voltage. Control voltage. Okay. So this control voltage is given as the input for the VCO. So here entirely in this PLL block, who is the main role here is the VCO. What is the full form of VCO is voltage controlled oscillator. Voltage controlled oscillator. Okay. Voltage controlled oscillator. So here generally we know what is the purpose of oscillator. What is a oscillator? The oscillator will generate certain amount of the frequencies based on the, generally for the oscillator, without giving any input signal, it will generate the output signal which is having the certain amount of the frequency. Whatever the frequency is there, the frequency of the output of the oscillator depends on the elements of the resistors, capacitors and the inductors, right? So here in this voltage controlled oscillator means here this is also a oscillator, but it can be controlled by the VC value. In what way it is controlling? Here, based on the VC value here, the output frequency gets changes. The output frequency gets changes continuously based on the VC value. Suppose if the VC is maintained as constant and same frequency F naught, same frequency will be present at the output of the VCO. Suppose if the VC value is continuously changing at the time, I will get the change with respect to F naught also, I can get the change. Okay. So mainly at what time it will change and at what time it won't change is till the corresponding frequency of the input signal is matched with the F naught frequency. My main aim here is I need to make the Fs is equal to F naught. Okay. F is equal to F naught. So the input signal frequency should match to the corresponding VCO output frequency. Okay. So till that, to make the condition of Fs equal to F naught here, this entire loop type of operation, the feedback loop type of operation will be done here. Okay. So now before giving the input signal, what will happen? Before giving the input signal for this phase detector, initially how the voltage controlled oscillator will generate if a signal which is having the frequency some F naught. How it will generate is, here initially before giving the input signal Vs for this circuit, the VCO will generate the corresponding frequency based on external resistor and the capacitor components. Okay. So based on the external resistor and the capacitor components, this voltage controlled oscillator, first initially it works as a oscillator. First it works as a oscillator because initially if I am not giving any Vs value at the time, the control voltage value simply equal to 0 at the initial case. At the time, how the VCO will generate the corresponding output signal which is having the certain amount of frequency is at the time based on the external resistor and the capacitor components, this VCO will generate certain amount of frequency F naught and the voltage of V naught can be generated, right? Later after that, I am giving the input signal Vs for the phase detector. Now the phase detector will do the comparison between the input signal frequency with the VCO output signal frequency and the amplitude. So definitely I can get Fs does not become equal to F naught. At that time, I can get the phase detector output is a error voltage and it will generate two different frequencies which is having the difference between Fs minus F naught and Fs plus F naught will be generated. So later it has been passed through the low pass filter. The low pass filter eliminate the high frequency components and it will allow only the low frequency components. Now due to this, whatever this input is Fs minus F naught which is having the error voltage V is that has been given as an input for the amplifier and the amplifier will amplify the input signal and it will generate the output voltage as Vc. In the initial case, I am having the Vc value equal to 0. Once if the Vc has been set at the time, now total control can be taken by the VC part itself now. Okay. So now based on the VC, now your VCO does not see what is the values of the resistance and the capacitance value because only one time we are setting the resistance and the capacitance value by externally. Once if the input signal has been given, automatically based on the control voltage VC here, this VCO will generate a new frequency component. Suppose if I consider the previous frequencies, F naught is the previous frequency. Now if there is a control voltage Vc is present, at the time, based on the control voltage Vc value here, either the frequency F0 can be increased or decreased, right? Frequency F0 can be increased or decreased. Suppose consider that the Vc value is high value I got. At the time, it will VCO will increase the corresponding output signal frequency from F0 to some F0 dash. Like that it will increase. Now, what are the new input that is coming from the for the phase detector is the new frequency signal of F0 dash, and the new output voltage of VCO is V0 dash. So this time this V0 dash and F0 dash is going as the input for the phase detector. Now again what will happen? The phase detector again it will do the comparison between the input signal frequency Vs, input signal voltage and frequency with respect to the VCO output of V0 dash and F0 dash. Now this time it will generate the output values of the phase detector becomes Fs minus F0 dash and Fs plus F0 dash. Now again your low pass filter will filter out the high frequency components and it will allow the frequency component as Fs minus F0 dash like this. And the error voltage and new control voltage of Vc dash now at this time I got, right? So here if I want to represent, this is a V dash I can represent, new values V dash and Vc dash. Now this new control voltage Vc dash will go as the input for the VSF VCO. Now consider that this time based on the control voltage Vc dash here, it has generated the new output voltage is V0 double dash, and here this F0 dash is changed to F0 double dash. This time this V0 double dash and F0 double dash both will go as the input for the phase detector. Okay, this time this phase detector will generate the new output frequencies Fs minus F0 double dash and Fs plus F0 double dash. Okay, so at that time the low pass filter output will be Fs minus F0 double dash and this error voltage VE double dash and here also VE double dash, and the control voltage value is Vc double dash. Just assume that this time I got the Fs value is equal to F0 double dash value. If Fs value is equal to F0 double dash value, I can get the control voltage value which is having the frequency of 0, because here Fs minus F0 dash, if I assume that Fs is equal to F0 double dash, at the time I will get the output of the phase detector will be Fs plus F0 double dash and another frequency value is 0, right? So at the time the low pass filter will generate the corresponding error voltage of VE double dash and having the frequency difference of equal to 0, right? So now here the control voltage I have represented is a Vc double dash. This Vc double dash is going as the input which is having the 0 frequency. Once it is having the 0 frequency, then your VCO can understand that the frequencies of Fs and F0 double dash both has been matched with respect to each other, and there is no need of a change with respect to frequency, right? So same frequency signal will be generated again. What are the previous frequency F0 double dash frequency that has been generated? Same frequency signal will be generated by the VCO also, right? So now again this time what is the phase detector will do here is, in addition to comparison of the frequency F0 here, difference in the frequency, it will generate the phase difference also. Phase difference also. Again, same looping type of operation to make the, already it has made the frequency values fixed. So once the frequency value is fixed, at the time this loop is said to be locked loop. This is said to be locked loop. Now this loop rotates to make the corresponding phase also has to be made as equal. So this time your phase detector will generate the corresponding phase difference as well as the frequency also. Now definitely we will get some certain amount of the phase difference. Now again low pass filter, error amplifier and control voltage I will get. Now this time based on the control voltage, it will make the changes with respect to phase, not with respect to frequency. Frequency is already set it properly, that has been locked. Okay, so now this is the basic operation with respect to PLL. If you observe here, basically there is a three modes are going on here, right? So one is capture range and one is the lock-in range. Capture range means whenever your VCO will try to reduce the difference between the input signal frequency with the VCO output frequency. Whenever this looping operation is going on to reduce the difference between the Fs and F0, that range is called as a capturing range. Okay. So next, once both the frequencies of Fs and F0 both are equal at the time, then it is called as a locking range. Yeah, let us go for those terms. And initially, before giving the input signal for the VCO is generating a corresponding signal which is having the frequency of initial frequency F0. How it is generating? It is generating the corresponding F0 frequency. Initially, we don't have any control voltage VC is not present at that time. So, based on the external resistance and the capacitance component, simply freely it is generating certain amount of the signal which is having the frequency of F0 type of frequency. Here generally this VCO output is a square wave type of output, not the sine wave, right? So here this signal, whatever this signal is there, this is having the frequency F0. This F0 can be set by the resistor as well as the capacitor type of components. Okay, so at that time we can call the VCO is the circuit is said to be in the free running state. Free running state. Free running state means without giving any input value. Without giving any input value. Simply your VCO will generate the output based on the external resistance and the capacitance. So that running mode is called as a free running state of the corresponding PLL. Okay, so let us go for the little bit more. Let us see the graphical representation of this one. Here. So here, if you see here, this is a circuit diagram which will represents the which is the y-axis is the low pass filter output, right? So and x-axis is the time period here. Now initially the mode is said to be unlocking mode. When this unlocking mode will be present is if there is a no input signal, if the input signal Vs is equal to 0 at that time, simply your VCO will generate the output signal which is having the frequency F0 with the external resistance and the capacitance type of components. So at that time we can call this as the unlocking condition. Now whatever this thing is there, this time I have given the input signal Vs has been given, right? So the the control voltage Vc has been generated based on the generation of error voltage passing through the low pass filter. After doing the amplification, I got the output of the amplifier is the control voltage, which is the input for the voltage controlled oscillator input. So whenever the VCO is generating, control voltage is generating every time, it is shifting the corresponding frequency. It is shifting the corresponding frequency. So always initially if you observe, the frequency value is high. Later, one loop of operation, slowly the corresponding frequency value is decreasing slowly. So in all these loops, what happened here? Entire loop operation of phase detector comparison, low pass filter, amplification, like this entire looping operation is going on. Always if you observe here, it is always trying to reduce the difference between the Fs and F0 value. Fs and F0 value. So this state is called as a capture transient, capture range or capture transient. Later, once the Fs equal to F0 is happened at the time, then we are calling this one as a locking range, locked. The circuit is said to be locked. So, as I shown you previously, the phase lock loop having the four components: phase detector, low pass filter, error amplifier, and voltage controlled oscillator. So simply the phase detector, for that we are giving the input signal Fs, which is having the phase, and the corresponding input signal frequency and phase can be compared with the VCO output signal frequency and the phase. So if there is any differences there between two signals, so the difference in the frequency as well as the phase will be present as a error voltage V. So basically this phase detector is a multiplier. It will produce as sum of the frequencies and the difference in the frequency Fs minus F0. So low pass filter, as I told you previously, it will remove the high frequency components and it will generate the output is the difference in the frequencies are generated at the output of the low pass filter. Again amplifier and again VCO. VCO means simply the VC shifts the corresponding frequency of VCO in a direction to reduce the difference between the Fs and F0 values. So if I go for the VCO initially it is a free running multivibrator and it operates at a set frequency of F0. This frequency F0 is called as a free running frequency. The free running frequency is set by the external resistor as well as the capacitor type of components. So the frequency can be shifted either side towards the positive side or negative side based on the control voltage VC, which is the output of the error amplifier. So here the frequency deviation is directly proportional to the control voltage VC value. So whenever the changes in the frequencies happen, that range is called as a capture range. So here the VCO continuously change its frequency till both the input signal frequency and the VCO output frequency both are same. Once both are same, at the time the circuit is said to be locked. Once the frequency is set, next time it will check what is the phase difference. Based on the phase difference, it will try to make the phase angle of the input and the VCO output signal frequency both are same. Like that the loop operation can be repeated. There are few definitions are there with respect to lock-in range, capture range. Already I have discussed with you regarding the lock-in range and the capture range, right? So now the next definition here is the pull-in time. So pull-in time is it is nothing but it is a total time taken by the PLL to establish the lock. To establish the lock is called as a pull-in time. So how much time it is taking to get the lock is called as a pull-in time with respect to PLL. It depends on which parameters. It depends on the what is the initial phase and frequency difference between the two signals. Two signals means input signal and the VCO output signal. And at the same time, what is the overall loop gain and what is the filter characteristics. What are the filter characteristics? Based on this, the pull-in time will be considered, calculated. Now, this is about the basic block diagram of the PLL. Right? Till now, what we have seen, what is the function of the PLL, application of the PLL. So, what is the internal block diagram of PLL? We are not going through each and every block, right? We don't know what is the internal circuit of each and every phase detector, low pass filter and VCO, yeah, like that. We don't know. Just we know what is the operation of each and everything, and based on the characteristics, what are the three parameters we should know. We learned till now there. Okay. So now the next part is we need to go for the internal block diagram of the PLL. So today I will cover the first block diagram. What is the first block diagram? Phase detector. So after completion of the phase detector, In the next coming sessions, I will cover the remaining low pass filter as well as the amplifier and the VCO, right? So let us go for the first block diagram symbol of the phase detector. Okay, so what is the basic function of the phase detector? The phase detector is a free running multivibrator which will work as a comparator, which will compare the difference between the input signal frequency with the VCO output frequency. Based on the difference, it will generate the output voltage of VE, which is having the two frequencies as sum of the frequencies, that is Fs plus F0, and the difference between the frequencies Fs minus F0 will be generated at the output of the phase detector. Yeah. So in this phase detector also there is a two types of phase detectors are there. One is the analog phase detector and another one is the digital phase detector. Analog phase detector. Analog phase detector means, what is the meaning of analog phase detector? So analog phase detector means the name itself it is telling. Based on what is the type of input signal we are giving for the phase detector, based on that analog phase detector or digital phase detector. So here I am giving the input signal is a sinusoidal signal I am giving. I am giving the input signal is a sinusoidal signal and the VCO output is a square wave. Here the input signal is a sinusoidal signal and the VCO output is continuously both for the digital phase detector and analog phase detector. In both the cases, we are having the VCO output is a square wave only. Only the thing is, the type of input gets changes. If it is the analog input, analog phase detector means I need to give the type of input signal is the analog input signal I need to give here, right? So when this here in the first condition, suppose if the phase difference between the frequency and the phase difference between the Vs and Ve value here, whatever the square is there, this is the this square is nothing but the VCO output, yeah, output of the VCO, and at the same time we are taking the one side, the sine wave is nothing but the Vs input signal sine wave I am giving here. Now when the VCO output is a positive square wave, when the VCO is positive square wave, at that time the switch is said to be closed. The switch is said to be closed. Whenever the VCO is having the negative square, if the phase detector is getting the negative square as the input from the VCO, at that time the switch is said to be opened. Okay. So for the positive square, the switch is said to be closed for the phase detector, and at the same time for the negative square, the corresponding switch will be gets opened for the phase detector, right? So at that time, if the switch is closed for the positive square, at that time what will happen? The corresponding switch will allow only the positive outputs at the output of the phase detector. Positive outputs at the output of the phase detector. Yeah. So what are the low pass filter is there? The low pass filter will generate the average value of the positive signal. Average value of the positive signal is this is represented as, here it has transferred the positive sine wave. So I will get the error voltage value also, average value of the error voltage also, positive error voltage I will get here. Okay, positive error voltage, right? So this is the positive error voltage I am getting. Then at that time, next time in the loop operation, now your VCO will understand that yes, I need to increase the corresponding frequency of the VCO output signal frequency I need to increase. That is the meaning of that. So next, suppose if the input signal frequency is having the phase of 90 degrees phase shift is there and the signal which is of the form like this. At the time when the VCO is a positive square, at the time it is allowing only the half of the positive sign and half of the negative sign it is allowing. At the time the error voltage value equal to 0. Error voltage value equal to 0 means at the time your VCO will understand that there is a no any change with respect to frequency is not required. Okay. Similar fashion, If the phase difference between the VS and the corresponding VCO output is 180 degrees phase shift is there. At the time when the switch VCO is closed, only the negative sinusoidal will be passed from one terminal to another terminal, and your low pass filter will generate the average DC voltage will come as the output of the low pass filter. At that time, this error voltage value is negative error voltage value I will get, which is the DC voltage I will get at the output of the phase detector. Yeah, average DC voltage. This is the negative voltage I am getting here. Okay, and at the time your VCO can understand that the frequency, output frequency of VCO has to be reduced. Like that it will consider. Okay, I think it's clear with respect to this phase detector of analog phase detector. Contrast to this, the next part is the digital phase detector. In this digital phase detector, if you observe here, as a physical digital phase detector, we are using the XOR gate. So for this XOR gate here, digital phase detector, why we are calling this one as a digital phase detector? I am giving the input signal frequency which is of the digital form, and the VCO output is also having the square type of signal I am getting here. So both has been given as the input for the XOR gate. Now what is the function of the XOR gate? If both the inputs are different, at that time I will get the output of the XOR gate is 1. If both the inputs are equal, at the time the output of the XOR gate equal to 0 0. Yeah, this is the XOR operation. If both are equal, at the time I will get the output value equal to 0. If both are different, I will get the output value is logic 1. High value I will get at the output. So to represent here, just I have taken this waveform. So here this is the input signal and this is the VCO output. In between these two, there is a pi is the phase difference I am getting here. At the time, if you observe the output, so both the inputs are not equal. At the time, I got the logic 1 at the output. If both are equal during this duration, I got the logic 0 at the output. Again 1 0, like this I will get continuously the DC output waveform. DC output waveform. This DC output waveform is depending on the what is the phase angle pi here. What is the phase angle pi? So let us see what is the maximum DC output voltage and what is the maximum phase angle that can be allowed by the phase detector. So here whatever this 4070 is there. This is a CMOS device, which is CMOS device, this IC which is having the 4070. So this is the waveform representation of the DC output voltage. If you observe here, the x-axis is the phase difference between the Fs and F0, and y-axis is the DC output voltage. So what is the maximum amount of DC output voltage? DC output voltage is nothing but the low pass filter average output value, right? So what is the maximum value you will get? For the maximum phase, if the phase difference is maximum value at pi, the phase difference between the input and the VCO output is maximum equal to pi, at that time I will get the maximum DC output voltage, error voltage I will get here, right? So in the remaining cases, I will get the phase difference value is less, I will get the voltage difference is also less voltage difference I will get here. So what are the slope of this curve is that the slope of this curve is represented as a k pi, which is nothing but the conversion gain. This is the conversion gain. So here, what is the formula for the conversion gain here is, suppose if I consider for the PLL I have given the supply voltage value equal to 5 volts is the supply voltage value I have given. At the time, the conversion ratio k pi is equal to 5 volts divided by 5 volt per radian. Suppose if the supply voltage value equal to, basic formula here is k pi equal to VCC by pi. VCC per pi volt per radian. This is the formula for the conversion ratio k pi. Okay. So it completely depends on the supply voltage of the VCC. Generally for the PLL we will give the supply voltage as the 5 volts we will give here. Right. So I think it's clear up to here. Right. So this is let us end up this module. So, today what we have seen, the basic function of the PLL, applications of the PLL, the internal block diagram, the description about the each and every block and the VCO basic operation, and at the same time we have gone through the first block of the phase detector. In the first block of phase detector, analog phase detector as well as the digital phase detector. These are the things we have covered today. So in the next coming session, let us complete the remaining blocks, that is the low pass filter, amplifier and the VCO. Let us see in detail, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.